And this is actually work in progress. As you'll see, we do have some results, but at least one of them probably can be improved a bit, and we're hoping there will be additional results to follow. This is a paper in a series that we've been writing on voting methods. We have a long-standing interest in voting methods. The emphasis in this paper will be on strategic voting, and I'll explain what I mean by that in a few minutes. So let me begin by talking about voting methods or voting rules in general. A voting rule is simply a method for making a social choice, or in the context of political election, electing a political candidate to office. And the idea is that social choice should depend on the underlying preferences of the members of society, or the voters in society, as expressed by their rankings of alternatives, or their utility functions for alternatives. We'll use the utility function representation. Let me give some well-known examples of voting rules, rules which probably are familiar to most of you. Probably the most widely used, although not necessarily the most widely applauded, voting rule is the one that's actually used in this country to elect members of Congress. It's used in Britain to elect MPs, and it's plurality rule. And the way it works is everybody votes for a candidate, and we simply choose as the winner the candidate who gets the most votes, even if that's short of a majority. This is sometimes called first past the post voting. Another well-known voting method is majority rule, or Condorcet voting, where we choose an alternative, provided it exists, that is preferred to each other alternative by a majority of voters. Then there is runoff voting, which is used in many countries around the world, and in particular in France for presidential elections. There, once again, voters vote for single candidates in the first round, and if there is a candidate who gets an overall majority, that candidate is elected. If not, we go to a second round where the two candidates who got the most votes in the first round are pitted against one another. In the second round, the majority candidate wins. Then there is rank order voting, which was put forward by Borda, so it's often called the Borda count. And in rank order voting, an alternative is assigned 1 point every time some voter likes that alternative best, 2 points every time a voter puts it second, and so on, and then we just add up points. So we add up each candidate's points, and whichever candidate gets the lowest point total, because low points correspond to high preference wins. Now, if we go back to my title page, I emphasized Condorcet and Borda because, as you'll see, the Condorcet method, Borda method, are the two heroes of this story. But let me mention one other.
But the Condorcet's ill-defined in a sense, right? Because
Well, it has to be extended. That is, if there is no overall winner, then we have to extend it in some way. I'll talk about that later. Let me mention one other voting rule, the utilitarian principle, in which we simply choose the alternative that maximizes voters' utilities. If voters are assigning cardinal utilities to alternatives, we can just add up those cardinal utilities and elect the candidate with the highest total. So, given that there are already a good many well-known voting rules and an infinity of other voting rules we could in principle consider, the natural question to try to answer is, well, which one should we use? Which voting rule should we adopt? And the way that the voting theory literature usually proceeds is to move back a step and first try to answer the question, well, what is it that you want out of a voting rule? And then the mechanism design question, connecting this paper to one of the themes of the conference, is, well, which voting rule or voting rules can we construct, can we design, which come closest to satisfying what it is we want? And the way that we express what we want is through a set of axioms or criteria that a voting rule should satisfy. This particular paper emphasizes non-manipulability or strategy proofness as an important criterion. The idea here is that we don't want voters to have the incentive to vote at odds with their actual preferences. We don't want them to have the incentive to vote strategically. And there are a number of reasons why this is viewed as an important criterion. The most obvious is that if voters are voting strategically, then in effect we're not implementing the voting rule that is under consideration. We're implementing something else because people are misrepresenting their preferences. So that's one objection. Another is that if a voting rule is vulnerable to manipulation, then we're imposing a burden, an additional burden on voters, because in that case they not only have to figure out what they themselves want, which presumably involves some costs of introspection, reading up on the candidates' positions, that sort of thing, but they also have to make guesses about what other voters are going to do, because in order to vote strategically, you have to formulate a theory about other voters' behavior. And to the extent that you have to guess what other voters are going to do, you have a harder decision problem. It becomes a game theoretic problem, not just an individual decision problem. So non-manipulability, for a variety of reasons, is a natural condition.
Is there a social norm problem here too? In that some people may feel conflicted about not. But
Yes, and to the extent that they do, they are going to be exploited
that's right.
by the others who have no such scruples.
Mm-hmm.
Exactly. So we might want to rule out non-manipulability to protect honest people. Unfortunately, and probably most of you here are familiar with this, there is a basic negative result about non-manipulability, and that's the Gibbard-Satterthwaite theorem, which says that as soon as we have at least three alternatives, there's going to be no voting rule that is always non-manipulable, unless we accept the idea of one person making all the decisions, of dictatorial
What's
rules.
wrong with that? It's like that dictator.
Well, now, wait a second. I thought I was going to be the dictator.
Let's vote on that.
What we'd like to point out, though, is that there's a sense in which the Gibbard-Satterthwaite theorem is overly pessimistic, and the idea is that in the formulation of the theorem, Gibbard-Satterthwaite imposed the requirement that a voting rule should never be manipulable, which is a very strong requirement. In practice, there may be some circumstances where manipulation could occur, but perhaps those circumstances are not very likely to arise. And so a natural follow-up question to the Gibbard-Satterthwaite theorem is, well, how can we find, or can we find voting rules that are non-manipulable as often as possible?
Is this just a probabilistic thing, or is there a situation where, since I might manipulate, and the conditions might exist, but I have no knowledge of whether it exists, because I don't know what your preferences are and what Don's are. So in that sense, it's not manipulable, or, because of my lack of information.
Well, I've used the term most often without defining what I mean by most often. So this question will be expressed more carefully in a few minutes. And that's what this paper is trying to do, to find voting rules that are non-manipulable as often as possible. So let me show you the basic model, which in most respects is just a standard voting model. There's one significant difference, which I'll come to very, very quickly. We'll begin with a set of social alternatives, a set of candidates. Think of this as the universe of all possible candidates who might run for office. And here's the respect in which we're going to differ from most of the voting literature. We're going to assume that, in fact, there's a very large set of voters, in fact, a continuum. And this is made for largely a technical reason, which I will come to. So the typical voter is a point in this continuum. You can think of the continuum as being the interval from 0 to 1. And we'll express the voter's preferences over alternatives, over candidates, by his utility function, his or her utility function. which just assigns a payoff to each alternative.
What unit?
Sorry?
What unit is being used in that utility function?
Utils.
I'm sorry?
Utils. Utility functions are
Well, you have a utility function and I have a utility function, but if I multiply yours by 20 and mine by 10,
right.
they're still utility functions. And so I'm asking how you...
Right. Well, that depends on the setting. There are some voting rules where you are asked, for example, to assign numbers from 1 to 10 to each candidate. So you can assign any numbers you want. In that case, we're scaling your utility function to fit in between the numbers 1 to 10. But there might be another voting rule where we're doing it from 1 to 50. So the unit will depend on the voting rule. And here's a technical restriction which is made mainly for convenience. Voting theorists typically find working with indifference where a voter is exactly indifferent between two alternatives a nuisance. It tends to complicate the analysis. It doesn't make things, it doesn't add terribly much enlightenment, and it does add to technical complexity, so we're simply going to rule that out. We're going to assume that voters have strict preferences. And
I mean, so that would rule out, I mean, that precludes this utility function being continuous in I, right? But if you only had indifferences on a measure zero set of voters, I assume everything is fine.
Sure.
Yeah.
Sure. And so we'll describe the entire society by a profile. A profile U sub box, where the box can be represented by any, can be replaced by any voter I, is just a specification of every individual's utility function. And a voting rule, or a generalized social choice function, assigns to each profile and to each slate of candidates Y a winner. So if the profile is U box, and if the ballot, the slate of candidates is Y, then F chooses a member of the voting ballot Y as the outcome, as the winner. So actually this is not quite right, because we could have a tie. We could have an exact tie. For example, if we were using plurality rule, there might be two alternatives that are ranked first by the most voters. And if we were using the Borda count, we could have two alternatives that had exactly the same point total and also the lowest point total. The point is that if there are lots of voters, exact ties with plurality rule, exact ties with Borda count, exact ties with the other voting rules that I was talking about are extremely unlikely. In fact, with a continuum, they're probability zero. They're non-generic. And that is the reason for using the continuum, so that we can get rid of exact ties. Another common way that this is done in the voting literature is to assume an odd number of voters, so that you don't have an exact split of the voting population. That I've always found to be a much more awkward way of handling the problem of ties. This, to us, seems more natural. So the correct definition is that the voting rule should choose an exact, choose a single winner generically. And as John pointed out, a lot of the other conditions that we're imposing here could be expressed generically rather than always.
Is generic specific to the F? So for each F, there's a measure, 0 set.
Yes, it doesn't have to be the same. And it won't be the same. It won't be the same.
Hey, I think I missed something, how you've got this parametrized family of utility functions. What have you assumed about how U varies with the parameter?
Nothing.
Nothing.
Yep.
But what if U of I always equaled the same was constant? I mean, so there's just one utility function, then ties certainly would be generic.
No. We've got a domain of utility functions, and in principle, we're allowing all possible utility functions that don't have ties, that don't have indifference. Now, because when we work with the set of all possible utility functions, we run into impossibility results, Gibbard-Satterthwaite. We are going to make restrictions, but I haven't got to those restrictions yet.
Actually, generic just means that a very slight change in the model and it disappears.
Exactly.
Slight depends on your topology, and that gets to really gets just to the question of what is the topology on the ties here.
So, using the notation the concepts that I've introduced, now we can define these voting rules more formally. So here is plurality rule. Because we have a continuum of voters, we can't literally count up the number of voters who like candidate A best, but what we can do is to look at the proportion of voters. So mu, which for those of you who are familiar with measure theory, will identify with Lebesgue measure, but for those of you who are not familiar with measure theory, can just think of the mu as corresponding to the proportion of the population who has a particular preference for candidate A. So plurality rule says that we choose the set of candidate A's who are preferred the most, ranked first, by the highest proportion of voters. And similarly, we can define majority rule, the Condorcet method, as the set of alternatives that beat each other alternative by a majority, that is, by at least half the population. Rank order voting, utilitarianism. So I said that the way voting theorists proceed is axiomatically. They first try to identify properties that voting rules ought to satisfy, and then see which voting rules satisfy those properties. One property that is difficult to quarrel with is the Pareto property. It simply says that if every voter agrees that candidate X is better than candidate Y, they like candidate X more than candidate Y, and candidate X happens to be on the ballots, then it shouldn't be the case that Y gets elected. It would be a pretty perverse voting rule that elected Y when X was available. Another basic property can be thought of as a fundamental property of democracy is that voters should in effect be anonymous. That is, if we take a profile and now we permute the voters. So we give voter I's preference ranking to voter J, and we give voter J's preference ranking to K, and so on. So in the end, we have the same rankings, but different voters have them from before. That shouldn't change the outcome. That's the principle of anonymity, and it basically says that voters' names shouldn't matter, only their vote should matter, and this is encapsulated in the principle one person, one vote. Yes.
Why do you pick such a proofness as the axiom which should be satisfied most often, but you impose other axioms in a non-ambiguous manner? So why don't you look for a rule which will satisfy better property most often, anonymity most often, and such a proofness most often?
Again, why don't you wait and see how we're going to address this most often. Basically, what we're going to do is we're going to ask for the conjunction of the properties to be satisfied most often. Just a footnote here. One of the major objections to the way that Americans elect presidents, that is through the Electoral College, is the fact that that method does violate anonymity because it gives people in different states different weights. Neutrality, again, a very typical assumption.
Eric, is there a second order? Could you go back to that previous one? Is there a second order version of the Pareto property? So, for example, there could be at most one rule for which that first thing is true, right?
What do you mean?
There's at most one rule that is unpreferred to everything, that is dominated by everything else. Either somebody prefers you to me or me to you. So there can't be two that satisfy that first property. Therefore, I should be, if everybody prefers you to me, then I should not be chosen.
Yes, that's right.
But then,
that
once I'm eliminated by that rule, then you may be next in line. So, I mean, does that property get
this has to be true for all pairs X,
No, I understand,
X and Y.
but one could impose that you want the voting rule to say that if I already satisfy that property and therefore should be eliminated, then it's applied iteratively to whoever would be then, I don't know what the opposite of the word preferred, but dominated by the remaining members of the group. I'm not coming through you. I can see that, right?
No. But I think this property already encapsulates what you want. You're never going to have anyone elected if there's another candidate out there that everyone likes more, and you can apply it iteratively.
Well,
or not.
that seems like that's another axiom to apply it iteratively.
No, it's not. It's exactly the same.
It's a consequence that he's going to be assuming on the preferences.
But, okay, well, all I'm saying is although I will never be chosen, people will still have the right to vote for me. So it's not the same.
You don't need, Simon, you don't need to proceed iteratively because this condition is always applied pairwise. So the existence or non-existence of some third candidate is not going to affect the fact that everybody prefers X to Y.
I should let this alone, but let me just
Okay.
say, suppose there are three of us,
Yes.
and everybody prefers you and Don to me, and everybody prefers Don to you.
Mhm.
But we're all in the voting.
Yes.
Then that same logic would say that I shouldn't be chosen and you shouldn't be chosen.
Right. And it does.
But,
It does.
well, why? I mean, it's not the case.
I can't be chosen because Don is there, and
Yeah,
you
I know,
can't
but
be
that-
chosen because I'm there.
But you are not eliminated by the Pareto property because
Yes, I am.
people do not prefer me to you.
No, I'm eliminated because Don's there.
Only after I've been eliminated.
No, even before. Even before.
If there's some
I
X.
can't be elected because Don is on the ballot, and everyone prefers Don to me.
The Pareto property has this transitivity property because voters have transitive preferences. And so it doesn't follow from the Pareto condition, but it follows by using the Pareto condition along with transitive preferences of voters. And that's what gives you the transitivity of the Pareto condition.
I'll let it go.
So neutrality basically imposes the same equal treatment that we have already imposed for voters to candidates. We want to treat all candidates equally, and the way that we do that is to say that if we have a profile, and now we permute the names of the candidates, so in people's preference orderings, then we should permute the winner, the name of the winner, in the same way. Now, all of the voting rules that I've been talking about satisfy the first three properties, and in fact, it's with some peculiar exceptions like the Electoral College, most voting rules that are used in practice satisfy the first three properties. It's the next property that typically knocks a lot of voting rules out, and this next property is far and away the most controversial property, in part because it is so good at getting rid of voting rules, and that's independence of irrelevant alternatives. Nevertheless, it does have some good arguments in its favor, and it has a very good pedigree. It was put forward by Ken Arrow and also John Nash, more or less at the same time. And it says this. I'm going to give the Nash formulation, but I could have done it the Arrow way. Suppose that for given voters' preferences and given the ballot of candidates, X is elected. And now we eliminate from the ballot some losing candidates. Well, they were, in a sense, irrelevant because they didn't get elected. So we ought to have the same winner. And that's exactly what Nash's version of independence says. And the political justification for this principle can be seen actually from a number of recent elections in American and French political history. Let's go back to the 2000 presidential election. You'll recall, I think people here are old enough to recall what happened 8 years ago. Everything came down to the state of Florida. The voting margin between Bush and Gore, the two leading candidates, was minuscule. It was less than 600. But out of nearly 6 million votes cast in Florida, But almost 100,000 people in Florida voted for Ralph Nader. Now we know from many different sources that an overwhelming majority of the Nader voters would have voted for Gore had Nader not been on the ballot. In fact, many other people who were inclined to vote for Nader ended up voting for Gore for precisely this reason. But still, nearly 100,000 people did vote for Nader, and so clearly Nader ended up changing the outcome of that election. Bush would have won quite comfortably. Gore would have won quite comfortably in Florida had Nader not been on the ballot. That somehow seems undemocratic. The idea that a fringe candidate like Nader, who got only on the order of 2% of the vote, should be able to change the entire outcome. And I won't go into the details, but people who remember the French presidential election of 2002 might recall that, again, another fringe candidate, although not quite so fringy as Nader. He got well, politically, yes. He got about 18% of the votes, a lot more than Nader. Jean-Marie Le Pen had a similar spoiler effect on the French election that year. So that's the political rationale behind independence. You can also object to it, and many people have. Well, majority rule and utilitarianism satisfy independence, but the others don't. So here's plurality rule. Let's suppose that there are 3 candidates and 35% of the people put X first, and then Y, and then Z, and similarly for the other 2 groups of voters. Notice that for this profile, X is the plurality winner because more people put X first than any of the other 2. But suppose that we throw Z off the ballot so that only X and Y remain. Well, then people in this third group will put Y first, and now we'll actually have a majority for Y, and so Y will be elected. That means that plurality rule, and this is actually an important argument that has been made against plurality rule. Plurality rule is highly susceptible to violations of independence. And rank order voting also violates independence. Here's a little example where the population divides in 2, 55% have the ranking XYZ, the other people have the ranking YZX. Y gets elected because although Y is in a sense in a minority, 45% of people put X all the way down at the bottom. So Y is a good compromise since the people who don't like Y as much as X put Y second. But if we get rid of Z, then X gets elected. And then it's a straight majority contest between X and Y. So one more axiom, and that's the one that prompted this inquiry, and that's non-manipulability. Because we're working with a continuum, of course, a single individual isn't going to be able to have an effect on the outcome, but coalitions certainly can. And so I'm going to express this as a coalitional requirement. It just says that it should not be the case that all the members of a coalition can gain by misrepresenting their utility functions. If they have utility functions UI, they can't all gain by voting as though they had utility functions UI prime. So those are the axioms. One point to make about non-manipulability, and this is well known, is that it immediately implies that voting rules should be ordinal. That is, only rankings matter, not the cardinal numbers that are assigned to candidates, because if a voter could change the outcome, or if a coalition could change the outcome simply by announcing a different utility function but with the same ranking, then it would be to that coalition's advantage. So, and here's a little proof of that, but I think the main idea is very straightforward. Unfortunately, majority rule also violates non-manipulability. Basically, for the reason that Simon already asked about, it's not always even well defined, because if we have configuration like this is an example of a Condorcet cycle. So the population breaks down into three groups. One group likes X, Y, Z. One group has the ranking Y, Z, X. The third group has the ranking Z, X, Y. There will be no candidate that beats the other two by a majority. So we have to extend what we mean by majority rule to cover Condorcet cycles. There are lots of ways of doing it. One way is to say that we choose a Condorcet winner if one exists, and otherwise we use the Borda count. That makes, but these extensions now make Condorcet vulnerable to manipulation. So here we have our Condorcet cycle. Under the Borda count, X turns out to be the winner for this profile. But if the middle group claim to have the ranking ZYX, then once again there's a Condorcet winner, namely Z, and now Z becomes the winner. So thanks to its extensions, Condorcet becomes vulnerable to manipulation. Now, unfortunately, there's no voting rule that satisfies all of these properties all the time, and that's Gibbard-Satterthwaite. And I formulated this a little bit differently from Gibbard-Satterthwaite, but essentially the proof is the same. But as my introductory remarks suggest, this should not be cause for undue gnashing of teeth, because there are many cases where, for good reason, we can expect that some rankings will not occur, or at least they are very unlikely, and therefore it's natural to to look for voting rules that work well when these unlikely rankings do not arise. So let's take majority rule, for example. Majority rule satisfies all 5 of these properties, provided that we're looking at utility domains where Condorcet cycles don't arise. So in other words, the only problem with majority rule is the fact that we could have a Condorcet cycle, that is, x, y, z, y, z, x, z, x, y can all arise in the same domain. And in fact, there are some quite plausible circumstances in which Condorcet cycles are extremely unlikely. Or, for example, let's think of the 2000 US election, where, as I already mentioned, the 3 candidates who got most of the attention were Gore, Bush, and Nader. Well, we can think of Nader as being the left-wing candidate, Bush as being the right-wing candidate. Actually, there was an even more right-wing candidate that year, Pat Buchanan, so we could add him to this picture. And then Gore was somewhere in the middle. It's not very likely that there are too many people who put Bush first, then Nader, and then Gore, or for that matter, Nader first, then Bush, then Gore. In fact, we have evidence suggesting that both those rankings, if they occurred at all, occurred in very small number. But that means that preferences were such that, and the formal term is single-peaked, so that Condorcet cycles are ruled out. We can also rule out Condorcet cycles if there is what can be called a strongly felt candidate. So in the French election of 2002, there were 3 candidates, 3 main candidates: Chirac, who was the incumbent, Jospin, who was the socialist challenger, and Le Pen, this ultra-right-wing candidate. People didn't necessarily have very heated feelings about Chirac and Jospin. They were quite mainstream, but everyone had a strong opinion about Le Pen. You either hated him, a lot of people hated him, or you loved him. You put him first or last, in other words. Whether or not this kind of polarization was good for France is debatable, but it actually is very good for majority rule, because if for every time you choose 3 candidates, there's one candidate that voters feel strongly about, you can also rule out Condorcet cycles. So let's define a voting rule to work well if it satisfies all 5 of these properties that I've been talking about.
5 minutes.
Yeah. When we restrict to some smaller domain of utility functions. For example, majority rule will work well if preferences are single-peaked, or if there are always strongly felt candidates. Then our first result that's about Condorcet, and it says there's a sense in which Condorcet works well more often than any other voting rule. Take a domain where some other voting rule F works well, then Condorcet must also work well on that domain. And conversely, suppose that Condorcet works well on a particular domain, and there's a profile where Condorcet and this other voting rule differ. Then we can find another domain where Condorcet works well and the other voting rule does not. So in other words, Condorcet dominates any other voting rule. If the other voting rule works well in a particular case, Condorcet must work well too. And furthermore, if the two voting rules differ, there will be domains where Condorcet works well and the other voting rule does not. And actually, this result follows from earlier work that Partha and I did, thanks to the lemma, which says that non-manipulability, in effect, implies ordinality. We had an earlier paper where we imposed ordinality, and we established basically the same theorem, but with ordinality and IIA rather than non-manipulability. So I don't have time to go through the proof, but it's not conceptually it's quite straightforward. But as I said, the most controversial of these axioms is independence, and there are good reasons for it, but there are also important reasons why we might want to drop it. And in any case, it's interesting to see what happens if we do drop it. And that leads us to our second result, which so far we have for the case where there are three candidates. Of course, this is of political importance because very often there are, particularly in American elections, there are three candidates. But we would like to be able to extend this. Probably other conditions will be needed too beyond three. Let's define a voting rule to work nicely. Do I have this here? Yes. But let's define a voting rule to work nicely if it satisfies the four conditions that remain once we drop independence on a particular domain. Once again, we can't get anything to work nicely all the time. That's Gibbard-Satterthwaite. But we have this second theorem, which says that jointly Condorcet and Borda dominate everything else. So take any voting rule, which happens to work nicely on a given domain, then either Condorcet or Borda will also work nicely on that same domain. Not necessarily both, but at least one of them. Furthermore, if this other voting rule differs from either Condorcet or Borda, then we can find another domain where Condorcet or Borda works nicely, and this other voting rule does not. So the two voting rules together, Condorcet and Borda jointly, dominate everything else. And I don't have time for the details, but one way of understanding the idea is the fact that there's a sense in which Condorcet and Borda complement each other very nicely. I already mentioned that Condorcet works nicely as long as we can get rid of Condorcet cycles. It turns out that Borda works nicely precisely in the case where we do have Condorcet cycles. So together, the two of them fill in the map, and that's where this domination, joint domination property comes from. Well, one satisfying feature of this result, at least for voting theorists like me, is that Condorcet and Borda are by far the most studied voting rules in the literature. They go back the farthest. They go back to the 18th century when Condorcet and Borda themselves were studying the, and they each have their proponents. Don is a well-known proponent of Borda. He's given very strong reasons in favor of Borda. I've tended to favor Condorcet. But this result says, well, there's a sense in which we can both coexist, peacefully coexist, because
I don't know.
It's striking that these two ancient voting rules emerge as dominating everything else. That I think is the moral I would like to draw. So thank you.
Is there a way to have a voting scheme where you require people to vote twice, once using Condorcet and once using Borda? And if they agree, then you take that result, and if you don't, you have some third mechanism to some kind of runoff.
Well, that formally speaking, that voting rule is already. These results apply to all voting rules, including ones which are combinations of Condorcet and Borda, and so this.
But there might be situations where C works exactly under those circumstances where Condorcet and Borda disagree.
You can characterize exactly where they disagree. It's possible now to characterize. In fact, Eric's comment in terms of Borda and Condorcet, in terms of the Condorcet cycles, if you go one step beyond that, and this is true for any number of candidates, for any n, that if you take a profile that has, in the linear algebra sense, the profile has no element from the Condorcet cycle, or n cycle, then what happens is the Borda and Condorcet outcomes and their tallies agree perfectly. They are exactly the same. So the only difference between a Condorcet outcome and a Borda outcome is due to one of these Condorcet cycles, at least in a linear algebra sense, being embedded inside a profile. Otherwise, it's ignorant if they're the same. And then the second comment, you talked about the IIA. Mathematically, you can show that one of the negatives of IIA, not in terms of value judgments or anything else, but in terms of mathematics on it, it's that the voting rule essentially treats certain profiles, such as those with a Condorcet, as coming from voters with irrational, i.e. cyclic preferences. And now you run into Simon's earlier question. Now you don't run into this transitivity of Pareto condition. But we know that from agenda problems, where agenda outcomes not Pareto security.
So you proved that that there's two rules that dominate everything else jointly, but are they the unique two rules? Could it be that there's another pair of rules that also have this property that they jointly dominate?
No. Well, put it. I didn't state these results as carefully as they should be stated. When I say that Condorcet, let's go back to the first result where Condorcet dominates everything else. Strictly speaking, that's not quite right, because we could formulate another voting rule which is exactly the same as Condorcet, except when there are Condorcet cycles. That is, there are multiple versions of Condorcet. There are, we could use Borda to break ties. We could use plurality rule to break ties. All of those are in the sense of the theorem, going to dominate the non-Condorcet voting rules. And in the same way, we could find different versions of Borda which do things differently in the case where there are not Condorcet cycles. But modulo that kind of multiplicity, there are no, Condorcet and Borda are uniquely maximal.
If I understood, that doesn't follow from the way you stated the result, though, right? Or does it actually follow from the statement?
I think it follows from the statement, because, oh no, actually it doesn't, you're right. You're right. It's a separate finding, yeah.
You did yours for three candidates?
Yeah.
In answer, John, in answer to you for three, he's completely correct, you aren't going to get it, but if you go to 4, now I can give you other axioms or conditions where you will get different rules.
Well, I was keeping the axioms the same, but wondering if you could find a pair of rules with the same property that.
Oh, I see.
Yeah.
Yeah.
You cannot, but you're right that requires more than the argument I gave. Yeah. Oh, question over here.
I like it, the Condorcet cycle argument, but I have a feeling that you can rule out those cycles because you have interpretation of the political spectrum on a line.
Mm-hmm.
So you would think that the extreme left wing would prefer a center left wing to an extreme right wing.
Right.
But this probably could be not always true. It's kind of a strong assumption. You could have like extremist kind of coalitionary national platform. I don't know. It's just.
Yes, and if that could happen, then you might violate the no Condorcet cycle property. That's right. I'm not asserting that in political elections we can always rule out Condorcet cycles. Merely that there are many historical examples where, with some confidence, we can assert that they probably didn't occur.